Uh, on the previous video, we said that a system's response to a unit step input was one way to come up with performance specifications or performance measures of the system. And in this video, what we're going to do is calculate those performance measures fairly exactly for a prototype second order system that is underdamped. In fact, we're going to calculate this peak point here and when it occurs. And as a side benefit, that will also tell us when these other peaks and valleys occur in this oscillation. We'll calculate the settling time, the 2% settling time, and we'll calculate this rise time, where how long it takes to go from 10% to 90% of the value. And of course, the final value itself, if you don't have an exactly prototype second order system. Before I get right to that, I want to talk about the critically damped and overdamped responses. Because if what you want is no overshoot at all, but otherwise you want the fastest response, what you want is this curve here, where the damping ratio is exactly 1. That's critically damped. All the underdamped cases, you'll have at least some overshoot. Any damping ratio between 0 and 1. You might ask yourself, why would you want overdamped? You're not always necessarily interested in the fastest response. Maybe the fastest response would overstress your system somehow. If you're talking, say, cruise control as an example, you don't want to floor it just to get to the speed you want. At least you shouldn't. You don't want to rev your engine, drive unsafely, etc. You want a controlled, slower. You don't want. There's probably some peak acceleration you don't want to go over. So in that case, you'd probably want an overdamped control system. But let's get back to calculating these values for the underdamped second order case. Probably before I go anywhere, if you have a pure prototype second order system, its final value is going to be 1. Prototype system was defined that way. But if it doesn't have omega sub n squared in the numerator, it can have some other final value. You would find that final value, or what it ultimately settles to, by using the final value theorem, which says just put 0 in for s in your the transfer function. We'll talk about that a little bit later. But first, this percent overshoot spec is the difference between this maximum value and the final steady state value divided by that final value. It's how much percent above that it is. And then once you have the percent, you can calculate this as an absolute number and the time it occurs. Let's look at that. This is one way to write the whole response of the prototype second order system to a step input. Okay, if we take its derivative and set it equal to 0, we're finding where the slope of that response is 0, right? Which would be right down here, up here at this peak, and then all these peaks and valleys. That slope is 0 or the derivative is 0. And we find that's when sine of omega sub d is 0, which means times are integer numbers of pi over omega sub d, the damped frequency. Here is where n equals 0, but the maximum would occur at n equals 1. These later n's are smaller deviations. So that is the time to peak, pi over the damped frequency. Or in terms of natural frequency and damping ratio, it's this formula. We're going to come up with a list of formulas. And then when we put this time to peak back up here in this guy, well, this sine part goes to 0. We're just left with this part. And this sigma, because t sub p, time will be pi over omega sub d. That's sigma over omega d pi, cosine of pi, which is just 1. So here we get that maximum value. You can either calculate that maximum value from this formula, or this gives you the percent overshoot. It's this e to the exponent here. As a percent, you multiply by 100. So we have percent overshoot, this formula. Or going the other way, since it's only a function of the damping ratio, if you give me a percent overshoot spec, I can calculate what the damping ratio needs to be. And as a side benefit, all these other peaks and valleys will be at integer multiples of this T sub P. So here's where T sub P is. This minimum occurs at 2 T sub P. This other little maximum, local maximum, occurs at 3 T sub P, etc. Our settling time. Instead of calculating exactly when the response gets within 2% of its final value and stays there, remember this oscillation occurs within an exponentially decaying envelope. We'll just use that envelope to calculate the settling. So here's the settling time. Here's our spec, 2%, which says this relationship must be the log of, natural log of 0.02, which is like 3.91 or minus 3.91. We'll call that close enough to 4. So our settling time is just 4 over sigma, or 4 over theta omega sub n. And if I call 1 over sigma the time constant, it's 4 time constants. So these relationships are the same as they were for the first order system, which is convenient. 4 over sigma, or 4 tau. This rise time, to go from 10 to 90% of the final value, it's a nonlinear function of zeta, the damping ratio. We'll use a linear approximation of that, which is this formula here, which uses both the damping ratio and the natural frequency. We'll use this most of the time in, well, I shouldn't say most. Here's another approximation. And by the way, some textbooks use this approximation, some use this approximation, some use other approximations, I guess. I didn't read all the textbooks. But this approximation is only a function of natural frequency. So we can reverse that. If you give me a rise time spec, I can come up with what the natural frequency ought to be. And the natural frequency is where the poles are. Omega sub n is the distance from the origin in the complex plane. So this gives me a circle in the complex plane, a semicircle in the left half of the plane, so we'll use this formula when we do graphs of where we want the poles to be. And we'll use this formula for almost every other case. What we end up with is a bunch of formulas to put on a formula sheet, which I let my students use for homework and exams. These first couple lines are just a way to relate these two sets of parameters, where we could have the transfer function either in terms of damping ratio and natural frequency, or in terms of basically pole location. Minus sigma is the real part of the pole, and omega sub d is the imaginary part of the pole. If I don't have a pure prototype second order system, I have some other constant other than omega n squared up in the numerator. I use the final value theorem to find where that final steady state value is. So it's just this k over omega sub n squared. We set s equal to 0. The rest are just formulas we put on a formula sheet. We have two different formulas for rise time. We'll use them in different places. And I think that's where I'll stop this video. We'll show how to draw a response, sketch a response in the next page.